Good day. Now let's discuss about the central limit theorem. So to remedy biases or failures for a sample to represent the population, polling organizations have since then resorted to using probability-based methodologies for selecting samples where the subjects are chosen on the basis of certain probabilities, which in turn allow us to compute for the number of respondents each sample respondent effectively represents. Randomization or using chance-based procedures for selecting respondents is the best guarantee against bias. In the previous videos, we learned the different probability sampling methods. So we learned also that when we gather the data from probability sampling methods, probability distribution data will most likely be normal. However, there are problems in which the distribution of data is unknown or not normal. So that's where the central limit theorem gets into the picture. So what is the central limit theorem? So from previous discussions, we have learned case 1. That is, if x is a normal distribution, then the sample means of the distribution also follows a normal distribution. Okay? Now this time, let's discuss case 2. That is, if the population from which the sample is taken does not follow a normal distribution, then the sampling distribution of the sample mean does not also follow a normal distribution. However, if the sample size is sufficiently large, so sufficiently large is a keyword there, the normality of the sample mean is guaranteed by the central limit theorem. So the CLT says that the sampling distribution of X is approximately normal if the sample size N is large enough. So to illustrate, we see here that as the number of the sample size increases, then the sampling distribution also tends to follow a normal distribution. So comparing n equals 1 to n equals 5 to n equals 16 and to n equals 20, okay, the difference of the distribution as the number of samples increases is very evident. So a good estimate of the mean is obtained if the standard error of the mean is small or close to 0, while a poor estimate is when the standard error of the mean is large. So to recall, we have learned that standard error of the mean is just equal to the standard deviation of the sampling distribution of means. Okay, so a good estimate is that if your standard error is small or close to 0, while a poor estimate is when the standard error of the mean is large. Thus, if we want to get a good estimate of the population mean, we have to make n sufficiently large. Okay? So formally, for any population with mean and standard deviation, or with population mean and population standard deviation, the CLT states that if the distribution of X is non-normal or unknown, again, if the distribution is unknown, the sampling distribution of all sample means is approximately normal for a sufficiently large sample size. The larger the sample size n, the closer the distribution of the sample means will be to a normal distribution. And how large is the sample size to be taken in order to get a good approximation from the CLT depends on the distribution of the population. In general, the sample size n taken should be greater than 30. And given the population mean and the population standard deviation, to convert sample means, okay, we have here x bar, so we have sample means to z-scores or to standard scores. We will use the formula z is equal to the sample mean, so the x bar there is sample mean, minus the population mean, all over population standard deviation over the square root of the sample size. Okay, so again, let's recall we have here x bar is the sample mean, the mu is the population mean, okay, this one is the population standard deviation, and n is the sample size. Okay, let's have this example. Suppose that a sample size of n equals 100. So you are given sample size is equal to 100. Is taken from a population with a mean of 500 and a standard deviation of 80. So let's find the following. Okay, so let's have this one. Alright, suppose that a sample size of 100, so we have already our given here, 100, is taken from a population with a mean of 500. So population with a mean. So meaning to say 500 there is the population mean. Okay? The 500 there is a population mean. At the same time, standard 80 there is the population standard deviation. So let's list all are given. Our n is 100. Our population mean is 500. Our population standard deviation is 80. Now, question A. Find the probability. Again, we are looking for the probability. So, now that we are looking for the probability, you already have an idea na. We should be using the Z table for this one. Okay? So, find the probability that the sample mean lies between 490 and 510. So, understand what is asked of the problem. Find the probability that the sample mean lies between 490 and 510. So, 490 and 510 is the range of our possible sample mean. So here we represent 490 as our x bar sub 1 and 510 as our x bar sub 2. It should be x bar because these are sample means. Okay? Not just an ordinary raw score. So it should be x bar. So you really have to read what is asked in the problem. So sample mean, so we have x bar. Since the sample size is sufficiently large, that's n is greater than 30, so by the CLT, the distribution is approximately normal. Then we will use the Z table to solve for this. So we convert the values of our x bar to standard scores. So again, back to our given, we have x bar sub 1 and x bar sub 2. So meaning to say we will need to find the corresponding z-scores of these two sample means. So we have using the formula, so z sub 1, this is for the corresponding z-score of x bar sub 1. So that would be x bar sub 1 minus mu over standard deviation, population standard deviation over the square root of n. And that is 490 minus 500 over 80 over square root of 100. That's equal to negative 1.25. And computing for the corresponding z-score of our x bar sub 2, so that would be 510 minus 500 all over 80 divided by square root of 100, that's positive 1.25. And going back to our problem, we are asked to find the probability that the sample mean lies between 490 and 510. So that would be the probability that our sample mean, so we have here our sample mean lies between 490 and 510. So this is just the mathematical way of saying find the probability that our sample mean is between 490 and 510. And since we have already converted our sample means into standard scores, then we can further rewrite this one into the probability of corresponding z-score of 490 is negative 1.25. So we'll have negative 1.25. Okay, that is now z already, because again, we have converted it already to z-score, to standard scores. And this one is the corresponding z-score of 510, which is 1.25. Okay? 1.25. So this one, this second denotation here is the basis for us on how are we going to solve for the probabilities later on using our z table. So again, how to read this one? This is a probability of getting a standard score that is greater than negative 1.25 but less than positive 1.25. Okay? So how to find the probability of the z-score to be between negative 1.25 and 1.25? So we will have to make use of these rules here, these summarized rules here. So without illustrating the curve, we can find for the area under the normal curve or the probability by using this one. So we have, okay, we just have to take note that the signs, no? The positive and the negative sign. Now let's go back to what is asked in our problem. So in our problem, we are asked of the probability of a z-score to be between or to be greater than negative 1.25 and less than positive 1.25. So look for the most applicable formula that we can use to solve for our probability here. Okay, so we can see that rule number 1 is the most applicable formula for what is asked in our problem here. Why? Because it follows the same format. We have corresponding the z-score, the probability of z to be greater than negative z-score. So we have negative 1.25, but less than positive z-score. So we have positive 1.25. Okay, so we will use rule number 1. So if we are going to use rule number 1, then that would be equal to the probability of z equals the negative z-score, where can we see this one? Where can we see these probabilities? Okay, in the z table, plus the probability of z equals the positive z-score. So all we need to do is to add the two of them. Okay? So okay, let's do that. So for our solutions, we have the probability of z to be greater than negative 1.25 and less than 1.25, according to rule number 1, is just equal to the probability of z equals negative 1.25 plus the probability of z equals 1.25. Alright? Now, at this point, I want you to get your copies of the z table. I will not show the z table here so that you will really get your copies of the z table. Okay. Now, using your z tables, find the corresponding z value of negative 1.25. So using the z table, we can see that negative 1.25 is just equal to 1.25, right? So that is 0.3944. So that means the area from 0 to negative 1.25 is 0.3944. And since we just have the same z value, so that would be plus the area from 0 to positive 1.25. That is also 0.3944. Adding the two, we'll get 0.7888. And since we are looking for the probability, then our final answer will be the probability that the sample mean is between 490 and 510 is 0.7888 or 78.88%. Now let's continue. So we still have the same set of given. Suppose that a sample size n equals 100 is taken from a population. So we know that our sample size n is equal to 100 with a population mean of 500 and standard deviation of 80. So here, find the probability that the sample mean is exactly 490. And and C, find the probability that the sample mean is more than 590. So here, let's write our given. N is equal to 100. Population mean is 500. Population standard deviation is 80. And our sample mean is, our x bar is 490. So for B and C, okay, our x bar is 490. So since the sample size is sufficiently large, that is n is greater than 30, by the CLT, distribution is approximately normal. So we will use the z table to solve for what is asked in our problem. So we convert the value of our sample mean to standard score. So we have Z is equal to 490 minus 500 over 80 divided by the square root of 100. So that's equal to negative 1.25. So alright, so for B, we are looking for the probability that the sample mean is exactly 490. So we're looking for the probability of the sample mean to be exactly 490. So since we have converted already our sample mean into standard score, so we rewrite this one. So this will be rewritten to the probability of Z to be equal to negative 1.25. Okay? So we are looking for now the probability of Z to be equal to negative 1.25. This is very easy. Using your Z table, find the corresponding area from 0 to negative 1.25. Okay, very obvious. It will give us 0.3944. So in here, we can already have our answer for letter B. So the probability of Z equals negative 1.25, or the sample mean to be exactly 490, is 0.3944 or 39.44%. Okay, so now let's go to C. So for C, we are looking for the probability of the sample mean to be more than 490. So we're looking for the probability of the sample mean to be greater than 490, right? That is the probability of the z-score to be more than negative 1.25. So here, without illustrating the curves, how to solve for this one. Okay, look for, again, let's write here it's the probability of z to be greater than negative 1.25. So find which rule will apply to finding our probability here. Okay, very good. That is rule number 5. Okay, probability of z to be greater than negative z-score. So that's negative z-score. So our way of solving will be 0.5 plus the probability of z equals the negative z-score. So going back to our problem, so here we'll have the probability of z to be greater than negative 1.25 is equal to 0.5 plus the probability of z equals negative 1.25. So 0.5 plus the probability of z equals negative 1.25, that is 0.3944. So 0.5 plus 0.3944, it will give us 0.8944. Therefore, the probability that the sample mean to be more than negative, to be more than 490 is 0.8944 or 89.44%. Okay, so that's how to answer questions B and C. Now, let's move on to our next part of the problem. So we still have, suppose that the sample size n equals 100 is taken from a population with a mean of 500 and a standard deviation of 80. So question, find the probability that the sample mean is less than 510. So first, identify your given. So we have n equals 100, population mean is 500, population standard deviation is 80, and the sample mean is 510. So since the sample size is sufficiently large, by the CLT the distribution is approximately equal. Then we'll use the z-table to solve for this one. So convert your sample mean, your x bar, into standard score. So we have positive 1.25. So we have positive 1.25. So let's write now. For letter D, we are looking for the probability that the sample mean is less than. So we have letter D, that is the probability that the sample mean is less than 510. Rewrite this one. This will be just be rewritten to the probability of Z to be less than 1.25. So the probability of Z to be less than 1.25. Now we'll use this one again to find for our probability. So we can use our Z table. So we have the probability of Z to be less than 1.25. Let's find how to solve this one without illustrating the curve. So let's write here the probability of Z to be less than 1.25. So let's identify which rule we can apply for finding the probability of this one. Alright, it's very obvious. We have rule number 6, the probability of a Z to be less than a positive z-score. So that is 0.5 plus the probability of the z-score. So let's use that one. Following rule number 6, we have the probability of Z to be less than 1.25 is 0.5 plus the probability of Z equals 1.25. So we have 0.5 plus, using your Z table, you know that P equals 1.25 is 0.3944. Adding the two of them, you have 0.8944. So meaning to say, the probability that the sample mean is less than 510 is 0.8944 or 89.44%. Okay. Next, let's have our second example. Suppose that the weights of adult males have a mean of 65 kilograms and a standard deviation of 20 kilograms. The distribution of the weights is unknown. Take a sample of 45 male adults, Find the probability that the sample mean is between 68 and 75. So you already have an idea how to answer this problem. So again, first, we need to identify what are given. So we have here sample size is equal to 45 because the problem says take a sample of 45 male adults. Your population mean is 65. Your population standard deviation is 20. Your x bar sub 1 is 68 and your x bar sub 2 is 75. So next, we need to convert the values of x bar to standard scores. So find the corresponding z-scores for x sub 1, for z sub 1 is, okay, this is the corresponding z-score of x bar sub 1, which is 68. So we have 68 minus 65 over 20 divided by the square root of 45. That will give us a value of approximately equal to 1.01. For z sub 2, we have 75 minus 65 all over 20 divided by the square root of 45. It will give us an approximately a value that's approximately equal to 3.35. So now that we have already solved for the corresponding z-scores, okay, let's write. So what we are looking for here is the probability of the sample mean. It's between, right? So it's greater than 68 but less than 75. Okay, so we write this one. This will become the probability of, okay, z-score. The corresponding z-score of 68 is 1.01. So we have 1.01. So z to be greater than 1.01 but less than 3.35. Okay, so we have two positive values of z-scores here. So looking for the rule that best applies to our problem, we have, okay, rule number 3. So the probability of z to be greater than positive z-score and less than z-score. So we will use rule number 3. Okay, so that means we need to subtract z-score 1 from the probability of z-score 2. So solving, we have the probability of z to be greater than 1.01 but less than 3.35. Okay, remember that our z-score sub 2 here is 3.35. So that's equal to probability of z equals 3.35 minus the probability of z equals 1.01. So using your z table, find the corresponding z value or the area from 0 to 3.35. So the p of z equals 3.35 is equal to 0.4996 minus the p of z equals 1.01. That's 0.3438. Subtracting, it will give us a difference of 0.58. Therefore, we'll say that the probability that the sample mean to be between 68 and 75 is 0.1558 or 15.58%. Alright?